Okay, welcome to part 2 of thermodynamic definitions. This one is done from my house again, not from school, because my battery ran out in school and I was just getting into my flow. So today we're going to look at thermodynamic definitions and then go on to the questions that I set you for homework. So we talked last time about these random definitions here. Delta H of hydration is where you take a gaseous ion and you turn it into an aqueous ion. In other words, take a gaseous ion and drop it into some water. We mentioned that this is an exothermic process. We do a lot more on hydration and solution very soon, so we talk a lot more about them. So I'm not going into too much detail. I was about to say on the last video that enthalpy of solution can be either exothermic or endothermic. Now the reason for this is that you have to break bonds in the solid and then you form attractions to the water, so there's a balance between exothermic and endothermic there. So we talk about this in the next topic. So the ones I'm going to talk about now, we're going to do bond dissociation enthalpy, and then these two at the bottom are going to be incredibly important for the next topic, which is Born-Haber cycles. So if you wanted to read ahead on Born-Haber cycles, feel free to do that. Right, bond dissociation enthalpy though. So this is one that you've known about since sort of GCSE time. Bond dissociation enthalpy is remember how these all start, the enthalpy change when 1 mole of, and it's always when 1 mole of something is turned into something else, or when 1 mole of something is formed. So in this case, bond dissociation enthalpy, which I'm just going to write down here, is delta H. I'll write BD for bond dissociation. They might call it DIS on there, DIS on there. Bond dissociation enthalpy is the enthalpy change when 1 mole of covalent bonds is broken in the gaseous state. So if you notice that a lot of the other ones that we came across earlier under standard conditions, in this case you have to watch out for the state symbols because everything must be in a gaseous state. So this I2 gas turning into 2I gases represents a bond dissociation, because you're taking I2 gas and you're breaking a mole. If you've got a mole of I2, you've got a single bond in there, a single mole of bonds to be broken. So you're breaking a mole of bonds. So even though you make two iodine atoms, you have broken 1 mole of covalent bonds. Right, so that requires a little bit of thinking about. If you break a bond, you will create 2 things, won't you? If I break this pen in half, break 1 pen, you create 2 pieces. So bond dissociation will create 2 different parts. So if I write something like this, CH4 gas, everything's got to be in a gas if you're using bond dissociation, becomes a carbon and 4 hydrogens, gas. We think, well, what have you done here in terms of bond dissociation? Well, bond dissociation is the enthalpy change when 1 mole of covalent bonds are broken. So what we've done here is we've broken, for every 1 CH4 molecule, we've broken 1, 2, 3, 4 moles of covalent bonds. So this here, which I've written above, we're snapping, so I'm just going to try and move this down. We're snapping 4 bonds, we're breaking 4 moles of covalent bonds. So this is actually 4 times the delta H bond dissociation of a CH bond. So with bond dissociation, you've got to state the bond that you're talking about. So that's 4 bond dissociations, because there are 4 bonds in 1 molecule. You've got to break 1, 2, 3, 4. Talking about this then, iodine gas to iodine, you might be aware that I2 is actually a solid under room temperature, standard temperature and pressure. So this, you might firstly look at that and go, well, that's I2 turning into 2I's. You might think that this equation is also a bond dissociation, but it's not, because of this cheeky little solid here. So in fact, to get from iodine solid to 2 iodine gases, you would firstly have to turn the iodine solid into iodine gas, and then into 2 iodines. This that I'm going to label X, that's the bond dissociation, gas to gas. What could you call this? Solid I2 to gaseous I2? Well, it's not atomization because you're not creating atoms. I would call this solid to gas. What happens when you turn a solid into a gas? Maybe vaporize it. That could be enthalpy of vaporization. Something like that. So I'm just drinking my brew. The point is that I2 solid to I2 gas is not the same as I2 gas to 2I gas. They are not the same. Clearly they're not the same. That is starting with solid iodine, that is starting with gaseous iodine. Only this one could be called a bond dissociation because it's the gaseous state. Alright, we'll do some examples of these later, which hopefully will help you understand that. The final two that I'm going to talk about are lattice enthalpy of formation and lattice enthalpy of dissociation. Alright, delta H I'm going to call lattice formation, and then delta H lattice dissociation. And these are very much to do with ions, because a lattice, the lattice that it's referring to is a giant ionic lattice. A giant ionic lattice which has got many strong electrostatic attractions between oppositely charged ions in a lattice. I know some people who aren't from the school actually watch these videos, which is nice of them. This is something that we use to help us remember how an ionic lattice is held together. Many strong electrostatic attractions between oppositely charged ions in a lattice, so MC Bockle. So, I'm just going to draw a lattice just so you remember. Lattices typically look something like this, where the positive and negative ions are next to each other. Now this is a simplification because a lot of lattices, for example Na2O, would have 2 sodium ions to every 1 oxygen ion. But I'm just simplifying it here. There are many strong electrostatic attractions between the oppositely charged ions in a lattice. Now the enthalpy of lattice formation is, let me just get that start bit up again. The enthalpy change when 1 mole of, because they all start off with that, the enthalpy change when 1 mole of, it says here, a solid ionic compound, solid, there's your state symbol, is formed from its, now I'm just going to write it like this, constituent gaseous ions. Constituent means the ions that it is made of. So for example, a solid ionic compound, well pretty much all ionic compounds are solid because they have many strong electrostatic attractions between the oppositely charged ions in a lattice. So here's an example, sodium chloride. If you were to write the equation for the lattice enthalpy of formation, it's 1 mole of a solid ionic compound, that's this, done that, is formed from its constituent gaseous ions. So sodium chloride lattice will be made from sodium ions, which are Na+. So you've got to know your charges on your ions, haven't you? But that's group 1. And chloride ions, which is Cl-, gaseous. Constituent gaseous ions. So what this is representing, it's saying, imagining a situation where you've got sodium ions whizzing about and chloride ions whizzing about, and then they come together to form a sodium chloride lattice. Alright, this is not how sodium chloride is formed, but it is a thermodynamic definition that you need to know. Imagining that you've got gaseous ions floating about and then they all just collide together to spontaneously form a lattice. Now, you're forming many strong electrostatic attractions between oppositely charged ions in a lattice. So you're just making new attractions. So that is going to be very exothermic, very exothermic. It will give out a lot of heat because you're just making bonds. All right, I'll do another example, lattice formation. So I'll think of a solid ionic lattice. Solid ionic compound may be calcium fluoride, CaF2. Solid ionic compound. Constituent gaseous ions, well, this is made of a calcium ion, which is in group 2. So that would be a calcium ion. And fluoride ions are F-, so you would need 2 of them. Please don't be that person who comes up with the F2- ion. Alright? You're trying to tell me there's a covalent F2 with a charge on it? No. Fluoride ions are negatively charged and you would need 2 of them. So you've got a calcium ion floating around as a gas or whizzing around as a gas and 2 fluoride ions. And then they all come together to make this 2 plus 1 minus 2 plus 1 minus lattice. Okay? So that's the enthalpy of lattice formation. The enthalpy of lattice dissociation, and that's exothermic. The enthalpy of lattice dissociation is the precise opposite of that. So think what the precise opposite would be. Just by looking at it, it would be starting off with a mole of lattice and forming gaseous ions floating around. So it's blasting apart a lattice. And if you want to blast apart a lattice into its gaseous ions, I hope you realise you're going to have to put energy indo. So that means it's endothermic. And in fact, it's precisely... So if it is exothermic, like minus 1250 in this direction, to go in this direction, it will be positive 1250. I hope that makes sense. It's the reverse process. So delta H lattice dissociation, to dissociate is the opposite of associate. If you associate with people, you come together. If you dissociate, you come apart. All right, I want to dissociate myself from my friends. You would stop calling them. All right, so lattice dissociation is where you start. So it's, what would the definition be? The enthalpy change when 1 mole of solid ionic compound, so exactly the same as the other, is what? So it was formed before, so it's broken apart into its constituent gaseous ions. All right, something like that. So I wasn't meant to do this, but I'm going to start with a picture. So you might have plus, minus, plus, minus, plus, minus, minus, plus. This lattice dissociation means you're blasting apart the ions from the lattice. You're breaking the many strong electrostatic attractions between oppositely charged ions in a lattice to form gaseous ions. So it's endothermic. So we can go NaCl, for example, 1 mole of solid ionic compound. That's the subject of this definition, forming Na plus gas and Cl minus gas. What's another one I could do? Potassium oxide, solid, forming K plus gas. There'll be 2 of them, and an O2 minus gas. Squeeze off the screen. So that's lattice dissociation. All right. So there they are. You might have to wind back through those 2 videos if you want to any help with them again. But hopefully we're now ready to look at the questions that I set you for homework. All right. I'm aiming to get through all of these, so feel free to skip through to the ones that you found difficult. But hopefully you're going to see me working through them and you're going to hear my logic. I know there's loads of people who just skip these videos. And you're putting yourself at a big disadvantage, actually, to those who do sit down and, spend an hour going through this. This will be about a sort of 25 minute video, and you should be pausing it and thinking and stuff like that. All right, enthalpy of formation. I'm going to say these definitions as I go. I'm not reading them. I'm just saying them, okay? I've learned them. It's not that hard. The enthalpy of formation is the enthalpy change when 1 mole of a substance is formed from its constituent elements with everything in the standard states. All right, C6H6, C6H6, it tells me it's a liquid. So we're looking for elements in the standard states. That's going to be carbons and H2s, 6 carbons, 6 carbons. Hydrogens are going to be 3 of them. That's a solid, that's a gas. All right, if I do make a mistake on these, I'm really sorry. I haven't got the answers printed out. I don't think I'm going to make a mistake though. The formation of CH3COOH, CH3COOH liquid. You've got to watch your state symbols on these. You get the state symbols wrong, you've just lost the mark. So constituent elements are carbon, hydrogen, which is H2, and oxygen, which is O2. How many carbons? 1, 2. 2 carbons. 1, 2, 3, 4 hydrogens, 2 H2s, and an O2. Boom, boom. Solid. Hydrogen is a gas. Oxygen is a gas. Everything's got a state symbol. That's correct. Combustion of H2. The enthalpy of combustion is when the enthalpy change when 1 mole of a substance is burned completely in oxygen with all the substances under standard conditions. So you've got H2 being burned in oxygen. What do you get when you burn hydrogen? You make water, H2O. Standard state, liquid, gas. Deal with the balancing at the end. H2, H2. I'm not allowed to change this number because it's 1 mole of this substance. So that means you're going to need half an O2. Done. Combustion of ethanoic acid, CH3COOH, or vinegar to you and me. Well, actually, no, ethanoic acid to you and me because we're chemists. Right, it's got carbons, hydrogens, and oxygens. You burn carbon, you make carbon dioxide. You burn hydrogen, you make water. These oxygens are just going to help it to burn. You can't make oxygen oxide. So then we go 2 carbons make 2 carbon dioxides, 4 hydrogens make 2 waters. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So remember to include those 2 O's there. Ooh. Liquid, gas. Standard state of water is a liquid. Put a plus in there. You just got some marks in your A level. First ionization. I'm just going to draw an arrow on all of these. Right, first ionization of aluminium. Ionization energy. First ionization energy. Right, is the enthalpy change when 1 mole of ionization, come on. When 1 mole of gaseous atoms, loses an electron. Come on, Norton. Got a little brain freeze there. It becomes that. Okay, and therefore by doing that. Okay. Phew, got there in the end. The enthalpy change when 1 mole of gaseous atoms loses an electron per atom to produce gaseous 1 plus ions, something like that. And then Al plus becoming Al2 plus an electron, 2 plus, gas, no gases, no marks. You'd be gutted, wouldn't you, in an exam if you missed that out? And you come out celebrating, telling me how easy it was, and then I ask you, did you put your state symbols in? And you go, I think so. But deep down in your heart, you know you didn't practice enough, and you probably forgot to do that. Isn't that sad? Alright, first electron affinity of chlorine. Right, electron affinity is the enthalpy change when 1 mole of gaseous atoms, Cl gas, atoms, so there's no 2 there, gaseous atoms, chlorine atoms, gains 1 mole of electrons per atom to become 1 mole of gaseous 1 minus ions. That's a new one for us, so one that we will do a lot with coming up. The lattice enthalpy of formation, so not delta HF, but delta H lattice enthalpy of formation. So we're going to be forming a lattice, sodium oxide Na2O. Alright, you know, when I told you at the start of year 12 you need to know your ion charges, this is why. Because otherwise you go through this and your biggest problem is actually writing down the formulas. Sodium oxide, sodium is Na plus, oxide is O2 minus, gaseous ions, 2 of them, 1 of them, tick. Lattice enthalpy of dissociation, delta H lattice dissociation. So you start off with a lattice, aluminium oxide is Al2O3. Do you notice I'm not thinking about that, I just know it. Aluminium is 3 plus, oxygen is 2 minus. So 1 mole of solid ionic lattice is broken apart into its constituent gaseous ions, Al3 plus gas plus O2 minus gas. Now I just need to balance it, but I'm not allowed to change the number on that because it's 1 mole of, so it's 2 of them and 3 of them. Right, hydration enthalpy of sodium ions, Na plus gas plus aqueous makes Na plus aqueous. Oh, that's a funny one. Enthalpy change when 1 mole of gaseous ions become dissolved in water. Okay, you can say become 1 mole of aqueous ions, which is fine. Hydration of oxide ions, O2 minus gas. Put them in water. We write AQ, not H2O. So then you don't have to balance the hydrogens and oxygens. Becomes O2 minus AQ. Alright, just moving the page up. That's just the change of state symbol from gaseous to aqueous. You know, hydration, if you hydrate yourself, you drink water, don't you? So I hope that's quite easy to remember. Solution of sodium oxide, this is about dissolving. So you take some sodium oxide, Na2O, which is a lattice, and it's solid, and you drop it into some water. Well, what will happen? You'll get ions floating about in water, so you'll get Na plus aqueous, Na plus aqueous, and you'll get O2 minus aqueous. Looks a bit similar to a lattice dissociation, doesn't it? But the symbols over here are aqueous and not gaseous as they were up here. But you're taking a lattice and you are dissociating it by dropping it into water. That's a way of thinking about it. Solution of magnesium carbonate. Magnesium carbonate, MgCO3, solid, plus AQ becomes Mg2 plus AQ plus CO3 2 minus AQ, the constituent aqueous ions. Bond dissociation enthalpy of water. Well, a lot of you will have looked at the marks on this. I don't like the question. I think it should say the bond dissociation enthalpy of the HO in water. Because the bond dissociation enthalpy is the enthalpy change when 1 mole of gaseous covalent bonds, 1 mole of gaseous covalent bonds is broken, or 1 mole of covalent bonds is broken in the gaseous state. So water, if I draw it out, if you've got a water gas, there's 2 of them, there's 2 covalent bonds in there. So you'll make an oxygen atom, which is O gas, and you'll make 2 H's, 2 H atoms. If you break this bond, snap, and you break this bond, snap, you're going to make an O atom and 2 hydrogen atoms. Alright, gas and gas. So I would write that as H2O gas going to O plus 2. But you've broken 2 bonds to do that, so you need half an O2. You'll then make half an oxygen and an H. Alright. If that one's giving you a headache, well, come back to it at the end and think about it again. But you've got to break 2 bonds to snap both the bonds in water. So to balance it for breaking 1 bond, because bond dissociation enthalpy is, you know, per mole of covalent bonds broken. So you have to halve that. Anyway, bond dissociation enthalpy of hydrogen is much more simple. Hydrogen H2 is a gas anyway, and it becomes 2 H gases. You go from H2, which looks like that, you snap that bond, you make H and H. That's all that means. Gas, 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 gas. Alright, atomization of bromine. Right, atomization is the enthalpy change when 1 mole of gaseous atoms is produced. So that's the thing that you put down first. Bromine, no Br2 because it's gaseous atoms produced from the element in its standard state. Bromine in its standard state is Br2, and you need half a mole of Br2 to make that. Standard state, bromine is a liquid. Alright. Atomization will cause you problems if you don't get your head around it. It's about producing 1 mole of gaseous atoms. Alright, if you're unsure of that one, go back to the first video in this pair. Phone battery's low again. Oh, goodness me. I'm down to 5%. So, bond dissociation enthalpy of bromine. Bromine, bond dissociation enthalpy is when 1 mole of covalent bonds is broken in the gaseous state. So I'm going to put a gas there, and I'm going to make 2 BRs. Gas. Alright, that's when you've got a BR and a BR forming a BR and a BR. So a bromine molecule forming 2 bromine atoms. Right, notice that these last 2 look similar. Alright. The atomization of bromine, though, produces 1 bromine atom from half a mole of bromine, liquid. The bond dissociation enthalpy, everything is a gas. Alright, and it's about 1 mole of bromine bonds, 1 mole of bromine covalent bonds being broken. So they're not the same, even though they look very similar. Okay, so you've got to get your head around the difference between atomization and bond dissociation. Oh, how long is this battery going to last? I don't think it's going to last very long at all. Okay, hopefully I can get through these. Vaporization. Now, people are worried about this vaporization one. I've had emails coming in. What do you reckon it is? Well, if you vaporize something, you turn it into a gas. So I imagine it's when one mole of bromine, let's go with that, Br2, which is a liquid at room temperature, probably it's when it turns into a gas at room temperature. So not breaking any bonds, you're just boiling it, like you'd boil water in a kettle and it'll turn into steam. It's when 1 mole of bromine liquid turns into 1 mole of bromine gas. That's what vaporize word means. It's not like some fancy chemistry word. It just means that in life. If you vaporize something, you turn it into a vapor from its standard state. First electron affinity of bromine. Bromine, for electron affinity is when 1 mole of gaseous atoms, each gains an electron to form 1 mole of gaseous 1 minus ions. Phew. Right, I'm going to have to stop there and charge my phone. So this is actually going to be video 2 of 3, and I'll see you all in part 3. Farewell.